So in terms of notes, we're in unit 4, valuations, and we're going to formally start doing what we informally started to do. We are going to do it slower because that will require to be slower. Oh. Okay. Yeah. So the most important definition here is the definition of valuation. Do you need some light here, or is it? Well, I don't have a light. I don't know what we need, but that's what it's going to have. Yeah. Okay, so we're going to define the notion of evaluation. And you should have in mind the evaluation that we talked about when you think of things, but it's going to be an abstract definition. So a valuation on a field F. So you start with a field. You should think of it as the field of rational functions, if you want. It's a field, some field. Is a map. So it's like this cool V. It takes an element which is a non-zero element of the field, and it produces an element in an ordered group gamma. It's always going to be Z from some point on, but not from today, because I can't argue that that's the case. So that's some ordered group. Sorry, what is what? This? How do you really call it? I think like a subnu, not sure. Yeah. It was like 4 years ago when I wrote the slide, so I don't know. Yeah, I should check and tell you. But I'm just calling it V. So it's a map, a V from the non-zero elements in the field to an ordered group. It doesn't have to be Z, but it will be. But not part of the definition, such that you need two properties, and that's the two properties that we saw hold for the cases that motivated this definition. So the first property is the notion of additivity. So you require that VAB, so you can multiply in the field, right? Apply V, you get an element in the ordered group. So I want it to be the same element as if it's a group, so you can add. Here you don't use the fact that it's ordered, just a group. So you can just multiply in the field, apply the valuation, same thing as applying the valuation, add. It's essentially saying it's a group homomorphism from the multiplicative group to gamma. So really what's written here in grown-ups language is that this is a group homomorphism. And that happened in the examples that we talked about. And the other thing that happened was the inequality. Remember the inequality that was there? And for that inequality, you need this to be an ordered group. So you want that V of A plus B is at least the minimum between the two. And when you look at it for a second, you just have to be a little bit careful, because even if A and B are non-zero, maybe this is zero, or maybe this is, no, well, this is not zero, but things could go wrong, and V doesn't eat something which is non-zero. So there is, for every A, B, such that for A, B that are non-zero, such that it's a weird way of writing it. A plus B is also non-zero. I don't know. Yeah, just to make sure that everything's fine. And you don't have to require that because both of them are non-zero. Just, for every A and B, which makes sense to say that. And in fact, it's going to be kind of annoying to keep saying for every A and B such that. So what we are going to do is to extend the notion of evaluation, and I'm going to extend it like literally extending on the board. So I'm going to consider evaluation to be from F to gamma union infinity. Like I'm going to add 0 here and infinity there with the infinity that we talked about from before. So of course, the only thing that's going to happen is that 0 will go to infinity. And I'm going to define, yeah, so once we have only 0 goes to infinity, and once we have defined that, we don't really have to say that anymore. We can kind of, if you add these purple elements here, you can remove the disclaimer. Think about it for a second, you'll see. Like, for example, if none of them is 0, everything's fine. But if maybe A is minus B or something, then and none of them is 0, then these are non-zero and this is infinity, and so forth. Maybe 2 more cases to check. But don't worry too much about it. You can just define 0 goes to infinity, and then you really have the additivity and the triangle inequality. Questions? So let's see an example, like 2 examples. Yes, please. If A is 0, then that's fine. If A is 0, okay. Yeah, like, good. So, like, 10 generations checked it. We can skip and trust them, but no, it's good to check. So here is an example. There are 2 examples, like family of examples. So p-adic valuations over Q, of Q. Oh, maybe I should say of. Okay, so here is an example that comes from number theory. You know it, even if maybe not by name. So, well, maybe the first example should be like always what, like even if you don't, I mean, it's like you can always say a thing, something. The first example is the trivial valuation. You don't even have to figure out what's trivial, just say it. But here trivial is just mapping everything to 0, except in 0, which is mapped to infinity. If everything is mapped to 0, then it encodes no information, but everything holds. So yeah, okay. Other than that, there's more interesting examples that are useful. So let's consider, let's fix P prime. Okay. And I'm going to define this evaluation that takes a non-zero rational number. We know what to do with 0, so a non-zero rational number. I'm going to give you an integer with the usual ordering. So in this case, gamma is the usual z. And I'm going to do the following. So in order to figure out where Q goes to, okay, so what I'm going to do is I'm going to just write Q as P to the n times alpha over A over B, where everything here is an integer and these are not divisible by P anymore. Right? You can just, because of the UFDness of the integers, you can just check how many P's are here, how many P's are here, put them here. And then what's going to be the answer? N. Right? Well defined. It's clearly additive, because when you multiply 2 numbers, the exponents adds up. And it's not hard to see it's also that, because if one has like P, so think of PA plus P squared. So P plus P squared is P times P plus 1. Right? So it's like you get a P outside, but not 2 P's. So you get the inequality. Okay, so for example, what is a -2? Because you just take how many threes you can. You have 2 threes at the bottom, so it's -2. Good, so that's a valuation that we'll never talk about, but it's a good example. Another valuation that we will talk about is obtained by doing something which may look weird initially, but actually from a commutative algebra point of view, it's doing nothing. So what we are going to do is we can replace Q with, you take just the rational function fields over the rational functions over some field K, some field. Okay, so instead of that, you have, and you take, instead of a prime number, what you should take or can take? Good. So you can take P of X to be, let me call it irreducible. It's the same thing in our case, but irreducible element, something you cannot factor. And now it's going to go from the field of rational functions excluding 0 to Z still. And you're going to do the exact same process, right? So given a polynomial Q of X or rational function, sorry, Q of X, you're going to map it to n, but now what is n? So it's the exact same thing when you add x's everywhere. You just write Q of X as P of X, your initial P of X, like the point that you care about, like that. And you can do that because the polynomial ring is a UFD, so you can take as many p's as you'd want, and yeah, and that's also a valuation. And you may want to check why this should be prime and why this should be reducible, but not now. And in the particular example where P of X is x minus alpha, like the irreducible element is of degree 1 and of this form. So what this number really is? What is V P of Q? Exactly. So it's a number of roots of pole of alpha in Q. Exactly. So because it's how many times x minus alpha divides this rational function, or including negatives. So V x minus alpha of Q of X, which we also write, by the way, in this case as V sub alpha. It's just easier if in these cases is the root or maybe pole multiplicity of alpha in Q. Okay. Now in the notes there is a little discussion about how valuation are related to absolute values. So you can read it if you want. We are not going to use it, and I'm just not going to say it. Okay, it's very simple and easy. But a valuation induces an absolute value, which is actually stronger than an absolute value. There is a stronger property there. The triangle inequality is stronger in a sense, and it's called an Archimedean absolute value anyhow. And some people think of valuations as measure of distance. So for example, the valuation of f minus g, or two polynomials or something, or maybe a minus b in two numbers, as the distance between them. And if this distance is small, then sometimes properties go through. For example, if you are maybe irreducible, then every polynomial that is close enough to is also irreducible and stuff like that. I'm not going to talk about it. It's kind of written there. Okay? We don't need it. In general, in the notes, there's a little bit more than what I want to say. Why is it equal to the, what do you mean by B alpha? Right, because when P is x minus alpha, here you have x minus alpha to the n. And so this n means the multiplicity of x minus alpha as a factor in Q of X, which is the definition of the root or pole multiplicity of alpha in Q. So like the second video that you have this one? Yes. Yeah, that's just a notation for that. Yeah, good. Yeah, so just like that. Other questions? Thanks. Good. So again, on the notes, I'm like more formal and everything's written. So I allow myself to be a bit less like, formal on the board itself, completely formal. Okay. So let's talk about basic properties of valuations. So I call it here claim 2, so maybe I should follow station here. So claim 2 tells you, basic properties we're going to use throughout. So let V be a valuation. So I'm going and considering the extended version from F to gamma union infinity. Okay, only 0 is sent to infinity. So let this be a valuation. Then, so we're going to have like 6 things I want to say about it and prove one of them. They're all easy, but only one of them is like non-trivial, and it's the most useful one. So it's nice coincidence. So the first thing is just kind of by definition, essentially, is this thing. And we said this is a homomorphism, so it should send the unit to the unit. But you can also like kind of reprove it. V of 1 is equal to V of 1, 1, which is V of 1 plus V of 1. And that's how you prove that homomorphism sends units to units. But you can do it, or you remember that that's what happens in homomorphisms. The second thing, which actually may confuse you a little bit initially, is this thing. I mean, you would think maybe you should have a minus here also. But no, that's fine. Right? Because, like, for example, how many times 3 divides a number is the same as how many times 3 divides the minus of the number. Right? So when you see this, think of like integers or irreducible polynomials or something. Right? Everything will make sense. Right? Like 5 divides 1 0 times. What can I write so that it will get the minus of something? Right, 1 over. That is true. And you can write it, V of A times A inverse is V of 1, which is 1, and you sum up, and one of them is minus of the other. But if 5 divides your number 3 times, then it divides the 1 of your number minus 3. The interesting thing is that, I mean, we always know, just as a reminder, we know, just remind you, that V of A plus B is at least the minimum of the 2 valuations, like the marginal valuations. And this item will tell you that if these valuations are distinct, then you get equality. So if V of A is not V of B, then there cannot be cancellations in a sense. It's actually good for you to think of examples where this is required. Like find 2 numbers or it's easy, 2 rational functions, 2 numbers is kind of easier, for which there could be equal and you can be larger than the minimum. But if they are distinct, if the valuations are distinct, then, and we're going to prove this thing, then actually the triangle inequality becomes strict, and that's called the strict triangle inequality. So I'm going to use the name, so strict triangle inequality, okay? So that's 4. And then there is well, 5 is just something I'm just going to use, so I don't want to surprise you, and I doubt it will, but that you can extend the triangle inequality to any finite number of summands, right? Because this can be induction, obvious. And 6 is that, I don't know, it appears like once, but if you have a sum which is 0, sum of elements in your field, I don't know, which is 0, and it's not a trivial sum, so don't trivial in the sense of 1 element even, then I'm claiming that there are at least 2 elements with the same valuation. Right, so if you sum up at least 2 numbers in the field elements, so it's not numbers, it could be actually functions, and you get 0, so there are cancellations, so it means that 2 of them, something has to get canceled, and kind of by this, cancellation will only occur with equal valuations. So the only way you can cancel things, cancel a function to 0, cancel a bunch of functions, sum them up to 0, some of them has to have the same valuations, because in different valuations, they won't cancel each other. Like polynomials, like polynomial degree 5, you cannot add polynomials of degree 5 and cancel a degree 6 polynomial. So that's easy. You should maybe just make sure to prove all of this, but these are very easy. And I'm just going to do 4 just to get used to the definition, and because it's really important, as I said. Questions? So can I trust that if I go too fast, someone will tell me? Yeah. Right, so you can prove this in several ways, but there is like the canonical way of proving these things. So let's do it like that. So proof of 4 of strict triangle inequality. So let's, they are different. So let's assume, just for without loss of generality, this is the smaller one. So assume the valuation on A is strictly smaller than the valuation on B. And we know the triangle inequality, right? We know that VA plus B we know by the triangle inequality that VA plus B is larger or equal than the minimum, and they have different valuations. So this means that this is strictly larger than V of. We know that this is larger or equal than V of A. That's the minimum. But we want to prove that there is a strict inequality. We want to prove that there is an equality, right? We know this because the minimum, now that we know that this is smaller than that, the triangle inequality just means that this is larger than V of A, and I just want to prove equality. So we know this, but we wish to prove here equality, right? Just to set things up. So like this is the smaller valuation. Triangle inequality tells us that this is at least the minimum between them, and that's the minimum between them in this case, but we want to prove equality under this assumption. So the only thing you really can do is the following. So you look at V of A, and you do this hybrid argument. So you do this thing. Look at this element, because you want to see A plus B. You can cook it up like that. And by the triangle inequality, you know that that's at least the minimum between V of this and V of that. Right? And of course, what is this compared to V of B? V of B, right? No minuses or something. That's one, maybe the second one here. Good. And now you just need to stare and see that you're done. Because you know that this, if this would have been larger than that, you want to prove that it's equal. If this, by contradiction, if this would have been larger than that, and because this is larger than that, you'll get a contradiction. Right? So unless you get equality here, you get a contradiction because this will be larger than the minimum of two elements which are larger than it. It's hard to do that. So if V of A would have been V of A plus B would have been larger than V of A, you get a contradiction. That's it. It's a little bit tricky because you need to set it up the right way and then to see when it's done. But otherwise, simple. Question so far? Okay. So what I want to say now, it's written as claim free, but it's an observation, is that evaluation by definition is defined from a field to an ordered group. Sometimes you'll be given a domain. You'll see we are going to get not a valuation from a domain to something because it's not a valuation by definition, but you get properties that you want from valuation from a domain. And all I want to say is that once you know the valuation domain, you know it's on the fraction field, or the fraction on the fraction field of the domain. So what I'm saying is the following. So let R be a domain, right? So a ring with no zero divisors. and gamma an ordered group. Now assume you have this function that looks like evaluation, but it's not, because the domain is a domain. Like, sorry, it's not a field, just a domain. But other than that, it's going to satisfy the property that you want, such that so you have the homomorphism. Well, you have this property. For homomorphism, I need like multiplicative group. I don't want. You have this property, and you have that V of A plus B is at least the minimum. You have the triangle inequality. It looks like evaluation. And of course, just to be clear, V of A is infinity only when A is 0. Okay. So what I claim is that then V can be extended in a unique way to evaluation on the fraction field of the domain, right? So you have a domain, you can form the fraction field. Even if you don't have a domain, you technically can form something like this, but let's start with domain. And this is what I claim. It's kind of obvious, I'll say that, but this is something that will happen. I don't want to say within the proof, well, we can now extend it. So I just want to point it out like explicitly. Right, and why is this obvious? I mean, at least there is a unique way you should check it's actually evaluation. So if I give you an element in the fraction field, so it looks like, A over B, or some A and B in R. And now I need to set up, to define V of A over B. But I don't have a choice because of this. I have to set it to be V of A minus V of B, because it's V of A over B, so it's V of A minus V of B, because of the inverses things that we talked about. So that's the uniqueness, right? If you have a valuation that extends this, it has to be, as I defined it, the only thing is you need to check its evaluation, but it's evaluation. That's obvious, and that's less obvious, but it's still obvious, just less obvious. You have to at least write something to feel good. Okay, so that's a little claim that we're not going to prove. And in the notes, you have the proof sketch that I just said. Questions? Are we fine with everything? It really is okay. So you see, we just kind of gave an upside definition and we proved little things about it. That's kind of essentially called algebra then. But what you should have in mind is that there is a kind of something going on. There is a story. You should think of these valuations as representing points. And the points could be prime numbers, there could be reducible polynomials, there could be x minus alphas, which is alphas. But these are we only work with the properties, not with the objects themselves. Okay, so one more little definition. So definition 4 here in the notes says that, so maybe before the definition, I'll just say that when we are given a valuation, then you can kind of always replace this with the image of the valuation. Maybe like that or something. You can replace it with the image of the valuation. So, if you don't want to be too strict, you can always assume the valuation is onto. Because you can just look at the right range rather than whatever cooked up range they gave you to begin with. So sometimes I'm going to do that without noticing. Okay. So in this definition, the definition is of a discrete valuation. So when the image of the valuation is isomorphic to Z, no, maybe it's 5Z, but isomorphic to Z, we say, and this is when I say isomorphic, I mean like with the order. Like this is the group, but an ordered group. So minus 5Z is not the same. Right? So when I say 5Z as a group, it's isomorphic to Z, but minus 5Z as a group is isomorphic to Z, but as a ordered group, it's not. Reversed. So when I write this thing, you should always ask, with respect to which type, and that's with respect to the type of ordered groups. So there is an ordered homomorphism between them, isomorphism between them. Okay, anyhow, it's not going to, get too real at some point, but just saying, we say that V is a discrete valuation. Okay, so turns out all our valuations are going to end up being discrete. They may be like 5Zs, but then we're going to normalize according to that ideology there.